So, chapter 13 discusses how artificial intelligence has been used to further investigate our human cognition. Um, and one such application of AI has been to investigate how we go about making decisions. The second half of chapter 13 goes more into some of the specifics of artificial intelligence that I really believe are outside the scope of this class. And so even though we're going to be talking about some of this content and it's within the context of this chapter on artificial intelligence, I want us to be thinking about the fact that artificial intelligence is an applied sort of science. And it's applied in that it's meant to be a reflection of the way in which humans go about thinking. So between the field of AI, stats, and cognitive psychology, we've come away with a general understanding of how we go about making decisions in everyday situations, as well as when we're in situations with higher stakes, when there's more writing on what we decide to do. And sometimes the best way to understand something is to study the ways in which errors and mistakes take place. So taking the kind of viewpoint of in order to understand normal functioning, sometimes it's really useful for us to study abnormal functioning. So we're going to watch a short video that's going to introduce us to some of the concepts that we're going to talk about in regard to our error-prone decision-making, because I think it does a nice job of giving us a brief overview of these various ideas.
What do you think is more likely? Someone dying from a shark attack or someone dying from a fireworks accident? To answer that question, you have to make a decision. In decision-making, we make a judgment about the desirability, or in this case, the probability of some outcome. If you're like most people, you used a heuristic or mental shortcut to make that decision. You may have thought about all the instances in which you've read about shark attacks in the news versus fatal accidents involving fireworks. That method is called the availability heuristic. You're using examples that readily come to mind or easily available in your memory. Most of the time, that's a very helpful shortcut, but unfortunately, our easily memorable experiences don't always match the real state of the world. In this case, even though you've probably read more stories about shark attacks, the risk of dying from one is about 1 in 3.7 million, whereas the risk of dying from a fireworks accident is about 1 in 340,000. A much higher risk, but usually much less publicized. Another heuristic that can lead us astray in decision-making is the representativeness heuristic. In this case, we judge the probability of an event based on our existing prototype, or general concept of what is typical. For example, say I tell you that a person named Linda is 30 years old, single, outspoken, and very bright. She majored in philosophy, and as a student, she participated in anti-nuclear demonstrations and organizations that fought discrimination. Now, which do you think is more likely? That Linda is a bank teller, or that Linda is a feminist bank teller? If you're like most people, you answered that she's more likely to be a feminist bank teller. Even if you don't know any feminists, or even anyone who's exactly like our imaginary Linda, she fits your prototype of how a feminist would act. She's representative of a feminist. And most of the time, the representativeness heuristic can help us make quick judgments. However, in this case, it leads us to something called a conjunction fallacy, which is when people think that the co-occurrence of two instances, being a feminist and being a bank teller, is more likely than a single one, just being a bank teller. Because statistically speaking, there are a lot more bank tellers than there are feminist bank tellers. So it's actually more likely that she's just a bank teller, even though your instincts are telling you otherwise. Now be careful not to get confused between availability and representativeness. When you're using the availability heuristic, you're thinking of actual memories that can come to your mind that are available in your head. With representativeness, you're not necessarily thinking of exact memories, you're thinking of a prototype of this idea. Okay, so we've talked about some heuristics that guide our decision-making processes. So now let's talk about some biases that prevent us from making correct decisions or from changing our decisions once they're made. One bias is overconfidence, which is just our tendency to be more confident than correct. You may have experienced this going into a test when you thought you'd ace it, but then you didn't know a lot of the information. And this overconfidence could be due to fluency while you're studying or the ease of processing. In other words, things might have felt really easy when you were studying in your room, but if you never tried to test yourself to see if you really knew the answers, then you might overestimate your ability to produce answers when you needed to. You may have also experienced overconfidence if you've ever been in an argument when you're positive you're right until someone shows proof that you're not. If you don't change your mind after you get this new information, though, then you're falling prey to the bias of belief perseverance. This happens a lot around election time. Whenever people hear something they don't like about their favorite candidate, they often ignore it or rationalize it away. Now, this bias is slightly different than something called the confirmation bias, which is when you actively seek out only the information that confirms your existing beliefs. So in our election example, you would be exhibiting confirmation bias if you only read stories that talked about how wonderful your favorite candidate was. But you'd be exhibiting belief perseverance if you learned about, but then ignored, information that you didn't like about your candidate. Another factor that can affect decision making is framing, which is just how you present the decision. For example, suppose I tell you there is a disease about to strike the population that will kill 600 people. However, there are two options for programs to combat this disease. If you pick option A, then there's a 100% chance that exactly 200 people will be saved. If you pick option B, there's a 1/3 chance that all 600 people will be saved, and a 2/3 chance that nobody will be saved. Which do you want to pick? Okay, now try this one. The same disease is coming through, and you again have two options. If you pick option A, then there's a 100% chance that exactly 400 people will die. If you pick option B, then there is a 1/3 chance that no one will die, and a 2/3 chance that 600 people will die. Now which option do you want to pick? If you're like most people, when the decision is framed in terms of how many people will be saved, you're more likely to pick option A, save 200 people for sure. But when the decision is framed in terms of how many people will die, you're more likely to pick option B, to avoid killing 400 people for sure. Even though saving 200 people is the exact same thing as letting 400 people die in this example, it seems better to pick that option when it's framed or presented in terms of how many people will be saved. Likewise, it seems better to pick an option that offers a chance of no people dying rather than to risk not saving some people. So hopefully this doesn't make you paranoid, but our decisions are not quite as black and white or even as consistent as we think they are. So next time you have to judge something, try to take a step back and consider all the factors that could be influencing your decision.
So most of the difficult decisions that we face and the plans that we try to make are made under conditions of uncertainty. So, I mean, after all, it wouldn't be a problem to try to decide which major you were going to declare if you knew exactly how your life was going to turn out on the basis of each available option, each option of major that you were maybe considering. So in an ideal case, you would simply look over all of the future outcomes and choose the option that led to the outcome that you preferred the most. But because people are rarely, if ever, in these kinds of circumstances where we have all of the information available to us and we can know so many details in advance, most of our real life decisions involve having to estimate what our chances are or what our odds are in terms of considering possible outcomes and events. And so to understand how people go about doing this, it's necessary first to understand some concepts that are related to the concepts of probability and uncertainty. So although there are a number of other interpretations that have a lot more complexity, essentially for our purposes, we're going to be thinking about probability as a measurement that reflects a degree of certainty that we have about an outcome. And so as you might remember from statistics and or experimental, probabilities are numbers that range between 0 and 1. So this is where 0 represents complete certainty that an event will not take place, whereas 1 represents our complete certainty that it will. And so values that are in between 0 and 1, what are called intermediate values, these can be thought of as corresponding to intermediate or middle levels of confidence that we have that a certain event will occur. So as an example, someone who says that the probability of an event is 0.9 is saying that he or she is very sure, though not 100% certain, that the event will take place. So generally, people who are untrained in probability theory, that is just sort of the average person off the street, they don't have trouble understanding what a probability of 0 means or what a probability of 1 means, right? Those are a lot easier to understand. What's more challenging are these intermediate values of probability. These are more challenging, especially if you haven't studied probability theory. So often people who are not as familiar with probability theory, their use of intermediate numbers, it really differs from this sort of theoretical way of going about things. And it's not hard. So like, for example, what does it mean that you're 30% sure of something? How does that differ from being 40% sure? So when we go from this sort of numerical probability theory to sort of more real life applications, we see that what numbers mean in the context of a real life decision, so what 30% means in comparison to 40%, it's not very intuitive. It actually can be really challenging. So a way to help us think about how probability theory understands the differences that exist between these more middle numbers that are closer towards the middle rather than the two extreme endpoints of 0 and 1 of probability is for us to think about these intermediate values as forms of gambling or of participating in a lottery. So for example, consider a lottery in which there are 10 tickets and you have purchased 3 of them. If the winning ticket is randomly selected, meaning that each of the 10 tickets has a completely equal chance of being chosen, then the probability of you winning that lottery is 0.3 or 30%. If you were to buy another of the remaining 7 tickets that were up for grabs in the lottery, then the probability of your winning would go up to 0.4 or 40%. And so the difference between the probabilities of 0.4 and 0.3, they correspond to 1 lottery ticket in this sort of example. And so again, if we kind of take this analogy of the lottery, it better helps us wrap our minds around what certain probabilities might mean. But again, in general, people's intuitions regarding the rules of probability theory are often really off the mark. So a researcher named Barron in 1988 offered the following example. And so I want you to think through it intuitively first. And then if you want, you can pause this lecture and see if you can run some calculations. So the example that was given was a 30-year-old woman discovers a lump in her breast and goes to her doctor. The doctor knows that only about 5 in 100 women of the patient's age and health have breast cancer. A mammogram is done. It indicates cancer 80% of the time in women who have breast cancer, but falsely indicates cancer in healthy patients 20% of the time. That is, it gives a false positive in 20% of the cases. So this 30-year-old woman's mammogram comes out positive. So what's the probability that the patient actually has cancer? Okay, so I'm going to go ahead and jump ahead and give you the answer. So the answer is 0.17 or 17%. Now compare this to what you just sort of initially estimated. Most people find that just basing it on sort of their intuition, their estimates are much higher, sometimes even 4 to 5 times higher than the actual value. And the calculation that's used to figure this out, it's a formula known as Bayes' theorem. You don't need to know that, but for present purposes, the point that I want to make, it's not going to require a detailed explanation of the formula. So in a more sort of common sense sort of a way, this is how you can get to the value of 0.17. So let's go back to the essentially the sample information that we have. So we have let's say we have a sample of 100 women of the same age and health status. So if we take this statistic of 5 in 100 having breast cancer, we can expect obviously that 5 of these 100 women are going to have cancer. And if we compare that to the accuracy, that is the percentage of the time in which we get a true positive from this mammogram machine, it's 80% of the time that there's a positive test given and that positive test is actually indicative of cancer. So if we go back to our 5 women in this sample who have breast cancer, that means that 4 of them should show a positive test if they go through this mammogram process, right? 4 out of 5 is 80%. So going back to our 100 woman sample, that leaves 95 women who should be expected to not have cancer. And of these women, 19 should be expected to have a positive result. And that is because this 19 is representative of the positivity and the positive. Sorry, let me go back. So of these 100 women, we know that 95 of them are expected to not have cancer. However, based on the percentage rate that this mammogram gives us, about 19 women will receive a positive result. So, and this is because, again, if we take 15 of the women who do not have cancer, and the women who do, then we have the 20%. And so essentially, four of the 23 people who have been given a positive test result, that is the women who do have cancer and do not have cancer, only four of the 23 people whose doctors called them and said that they actually have a positive test result actually have cancer. And we find this by dividing 23 into four. And so, of course, the probability estimates can differ from one person to the next, or from one time to the next, right? Even though we're talking about general sorts of patterns, this doesn't mean that we are as predictable and consistent as we would like. So for example, when I'm in a bad mood, my estimates of the likelihood of success in one of the things that I'm trying to do is probably going to be a lot lower than when I'm happier. Additionally, my more optimistic friends, they always seem to find successful outcomes to be more likely than do my more pessimistic friends. And so for these and similar reasons, psychologists often distinguish between subjective probabilities, which are influenced by the characteristic of the person who is estimating the probability, and objective probabilities. And these objective probabilities are not under the influence of characteristics of the person making them. And of course, many real life situations that we might think about are likely to not have objective probabilities available, right? Because at that point, it's just humans making these decisions. And as we know, our cognitive abilities can be influenced by a number of things. So now we're going to move on from talking about probability to talking about how people gather the information that they use to try to make a decision. And so often the information comes from their own memory. So students who are choosing a major, for instance, they may have to think back to their experiences in different courses, or think back to things that they've heard other students say about their experiences in different majors. And so once the information is gathered, then the decision maker has to decide on the importance and the relevance of each piece of information as well. So if you don't care about becoming a biologist, for example, then the information that you've gotten about the different courses that are taught in the biology department, possible study abroad programs, things like that, you might not give that information a lot of importance because it doesn't align with ultimately your decision-making process. And so the way that people go about gathering and assessing the relevance of different pieces of information is going to be the focus of this next portion of the lecture. So research on people's decision-making skills and styles has pretty consistently demonstrated to us that the existence of certain systematic and common biases are sort of inherent to the ways of thinking that often lead us to making systematic errors. And typically, the biases that we see are understandable, and they're often justifiable ways of thinking under other conditions, but they can sometimes lead to errors when we misapply them. And so these sort of systematic biases have been called cognitive illusions. And the term itself is meant to sort of make us think of perceptual illusions, right? So the errors of cognition that come about for understandable reasons and that provide us with information that helps us understand normal functioning. So again, this idea that we're looking at the abnormal in order to help us better understand the normal. And so in a similar sort of way, the errors in decision making that we can study, they tell us something about the ways that people gather, sort, and integrate information that they use for making a choice. And the cognitive illusions that we're going to talk about also give us information on when our decision making is likely to be optimal in the face of not having a lot of information and in the face of uncertainty, and when our decision making might result in less than desirable outcomes. So, what is a cognitive illusion? Researchers by the name of von Winterfeld and Edwards, they specified that something counts as a cognitive illusion if it has the three following elements to it. So first, we have the element of there being a correct way of answering a question or going about making a decision. The second element is the existence of there being, in addition to a correct way, there also being a more intuitive kind of estimate or decision that can be made. And then finally, a discrepancy, a difference between the correct answer and what is intuited, that always goes in the same direction. That always leads us down the same sort of path. So answers then that have random sort of fluctuations, that is, they don't always lead us in the same direction, or situations in which there are multiple possible correct answers, then don't count as a cognitive illusion. So I apologize that the text on the slide is small, but I was trying to get all of this to fit nicely on one slide so that we could go over it and talk about the different problems that are shown here. So I want you to pause this lecture in order to read over these three problems that are on the slide and just come up with your first intuitive response to each one before you continue on in the lecture. Okay, so researchers by the name of Tversky and Kahneman in 1973 presented problems similar to these ones to undergrad students who were participating in their study. And overall, their findings were that people's intuitions were pretty systematically wrong. And so in problem 1, for instance, the letter L occurs more frequently in the third position than in the initial position or the starting position. And so in problems 2 and 3, the A and B options, they actually have the same number. So that is the same number of committees, the same number of paths. So let's talk about what accounts for these errors. So Tversky and Kahneman argued that when we're faced with the task of estimating the probability or the frequency of something, we tend to rely on shortcuts or rules of thumb known as heuristics to help us make these judgments easier. Again, going back to this idea that we've encountered before, where we have limitations to our cognitive abilities, right? We have limits to our working memory. We have limits to our attention. We have limits just to our mental energy in and of itself. And so one such heuristic or shortcut is known as the availability heuristic. This is defined as assessing the ease with which the relevant mental operation of retrieval, construction, or association can be carried out. So in other words, instances that are more easily thought of, remembered, or computed stand out to us better in our mind. And these are instances that are particularly salient or important, and thus we then come to deem as more frequent or more probable. So let's go back to the previous slide and talk through these problems. So in the first problem that's listed here, it turns out that it's a lot easier to think of words that begin with L, such as lawn, leftover, licorice, than to think of words that have L as the third letter in them. So for example, bell, wall, ill. And the reason for this likely stems from the way that our lexicons, our mental dictionaries, are organized. So they are more likely than not organized alphabetically by the first letter. And so this means that it's easier for us to search for words based on the letter that they start with than by the letters that make up sort of the interior portion of that word. So in problem 2, Tversky and Kahneman argued that two-person committees are more distinct. So there are 5 two-person committees without any overlap in membership, but any two 8-person committees will have at least some sort of overlap. Distinctiveness then makes different committees easier to think of. Therefore, thinking about two-person committees are more available to you because of this distinctiveness. And because of this distinctiveness, you take the shortcut and you think, well, there must be more of them, right? They must be more numerous in comparison to an 8-person committee. However, in this example, 2-person and 8-person committees are equally as numerous. So there have been everyday sort of analogs or comparisons that use the availability heuristic that have been studied. So as an example, Ross and Sicoli, they surveyed 37 married couples, so husbands and wives, and they surveyed them together and then separately about the estimated extent of their responsibility for various household activities, so such as making breakfast, getting groceries, caring for kids. And these husbands and wives were both more likely to say that they had greater responsibility than their spouse did for the majority of the activities, or the majority of these responsibilities, which we know is statistically unlikely, right? Like 2 people can't independently take care of 80% of things around the house. And so, moreover, in addition to this, when these people were asked to give examples of their contribution and their spouse's contribution to each activity that was being asked about in the study, each person listed more of their own activities than the activities of their spouse. So essentially, they're giving themselves more credit and giving their spouse less. And so Ross and Sicoli, they explain these findings in terms of the availability heuristic. So our own efforts and behaviors are often more apparent and available to us than are the efforts and behaviors of other people. So after all, we're certain to be present when we're performing an action, right? We are, even if you're sleep deprived, you're still going to have some level of conscious awareness, right? When you perform an action, but you may not have that same sort of cognitive presence and awareness when a friend or a spouse or a roommate carries out a particular action. So our own thoughts and plans are important to us, and we might be formulating them or focusing on them just at the same time when someone else does or says something. And this distracts us really from appreciating the extent of their contribution. And I say appreciating, maybe a better word would be attending to. And so in general, what we do, think, say, or intend is more accessible to us than to anyone else. And it's more accessible than anyone else's plans, thoughts, words, intentions. And so it's not surprising then, going back to the study, that in joint ventures like taking care of things around the house, each person feels like she or he shoulders a greater share of the burden. So availability can be both an efficient and effective heuristic for us. So if we can be sure that the ease of constructing something or calling instances to mind is unbiased when we're going about making decisions, then this would probably be one of the best or possibly the only tool for us to use when we are judging frequency or probability. And this is because of its efficiency and because of its effectiveness. So if you're trying to decide which course you typically write more papers for, psychology or philosophy, it's probably fair to judge the frequency of the papers by trying to recall specific paper assignments for each course. So in this case, there's probably no particular reason to believe that psychology papers, for example, are more memorable than philosophy papers. So if there is, right, if there is something that biases us in a way, so for example, let's say you take a philosophy class 3 years ago, your freshman year, to satisfy a GE, but you're taking all psych classes this semester, then that comparison probably isn't fair. There is a bias in the information that you're drawing on. So if you're trying to decide which occurs more often, the hours that you spend working on a group project or the hours that someone else in the group spends working on the same project, using this availability heuristic is going to be unfair because you are working with biased information. So you've been there whenever you've worked on things, both in the context of, maybe the in-person or via Zoom group meetups, the lab breakout times, let's say, using the research project for this class as an example. You've been there for the group chats and emails and things like that. But you might not have been there all the other times when other group members were working. particularly working sort of behind the scenes, working on the project without your sort of explicit knowledge that they were. And even if you had been there sort of with them every step of the way, you probably would have been paying more attention to your own work and your own planning than to the people in your group and what they were working on, what they were planning, what kinds of thoughts and ideas and questions they were coming up with in that moment. Therefore, examples of your own work are likely to be more memorable and more available to you than examples of anybody else's work. And so the point of discussing the availability heuristic, I mean, aside from covering the content of the course, it's not to warn you away from its use, but instead, as is the case with all other heuristics, all other mental shortcuts and conclusions and assumptions that we are likely to jump to, the idea here is to think carefully first about whether the range of examples that you're drawing from is equally accessible. That is, are you drawing on examples that are low in their bias? Are you drawing on information that is as unbiased as it possibly can be? So really just stopping before acting on information that might come to you through the availability heuristic, and consider possible other ways of understanding what might be going on. So that's where we're going to stop for today. We're going to continue talking about some other heuristics that can sometimes get us into trouble when we are making decisions on Wednesday.